Okay, now let us look at the heat engine. What is a heat engine? In order for the heat engine to convert heat to work, it must have two reservoirs. So this is one reservoir, which is high temperature, or we call source, and this is the other one, reservoir, the other reservoir, which is low temperature, or what we call sink. The device that convert heat to work, they receive heat from high temperature, so they receive this heat from high temperature. For example, they receive it from solar energy, oil furnace, nuclear reactor, etc. Then they convert part of the heat to work, and usually in the form of rotating shaft. And then they will reject the remaining heat, also we call as waste heat, to the low temperature sink, which will be the atmosphere, river, or etc. Okay, so this operation will be a cycle. So heat engine and other cycle devices usually involve fluid inside the system or the heat engine, and the fluid is going to or from which the heat is transferred while undergoing a cycle, and this fluid we call as working fluid. Working fluid. Okay, we can look inside the heat engine, which have boiler, turbine, condenser, and pump. If you remember when I was explaining about aircon, okay, also have, or the chiller system also have most of this component, but in a air condition they won't have turbine, and the pump is usually being replaced by a compressor. Okay, one of the example of heat engine is the steam power plant, and this is how it works. It receives heat from energy source, and this heat uh, input to the system by boiler, and then as we said just now, they have working fluid, so this working fluid is circulating inside the pump heat engine with this direction, the arrow direction. So a portion of the work output of the heat engine is consumed internally to maintain continuous operation. So there's a work produced by the turbine, and other than the waste used in the turbine, it will also be released by using condenser, and it will be released to a reservoir or energy sink. So the working fluid will be circulating the system due to the pump operation, and this pump usually being operated by electricity. So the use of electricity we will call as work into the system. So Q in is the amount of heat supplied to the steam boiler. Q out is the amount of heat rejected from the steam in condenser, and work out is the work delivered by the steam in a as it expands in the turbine, and the amount of work required to circulate the water to the system will be the work in. So work net, that is the output, will be work out minus work in, or it also can be calculated by taking the total of Q in minus Q out. Okay, for this heat engine, usually if you want to see the performance, we will say the thermal efficiency is the index of performance of the work producing device or the heat engine. So if you want to see the performance of the heat engine, you will see the thermal efficiency, and the ratio of net work output, which is the desired result, to the heat input, which is the cost to obtain the desired result, will be the thermal efficiency. So thermal efficiency is the desired output divided by the required input. Okay, so if this is the heat engine, you will know that we have Q in and we will have work out, and this heat will be the heat out, and the electricity power will be the work in by the pump. So the thermal efficiency will be the work net, or the output, divided by the Q in. Okay. So cyclic heat engine operate between high temperature, this one, high temperature reservoir, which is the source, and low temperature reservoir, or the sink. So if you want to calculate the performance of the heat engine, usually we see the heat engine, the Q net in is QH minus QL. If we Q net in minus the W net should be equals to 0. So meaning to say that if you want to calculate the work net out or the work output, we can say that the work output will be equals to Q in minus, this is Q in minus the Q out, QH minus QL. So the efficiency will be work net output divided by Q in, where the work output is Q in minus Q out divided by the Q in. So as a result, this will be the thermal efficiency of a heat engine. It's equals to 1 minus Q in per Q out per Q in, or we can say that this also equals to 1 minus Q low divided by QH, or Q high. Okay, this is a example. If we have heat source here, and usually some heat engine performance will be better than others. So if we see here, this is heat engine 1 and this is heat engine 2. For example, the heat engine 1, they both have the same input, the heat input, but heat engine 2 have work output of 30 kilojoule, and it will release the waste heat of 70 kilojoule, where the heat engine 1 work output is 20 kilojoule and the heat release is 80 kilojoule. So by this we will see the heat engine 1 is only 20%, but the thermal efficiency of heat engine 2 is 30%. So for example, if you have furnace going to a heat engine, and the heat engine converted the heat in to work output, that is 55 megajoule. So the heat release is 100 minus 55, that will be 45 megajoule. So even the most efficient heat engine usually rejected almost one half of their energy they receive as waste heat. So they only use about 50%, or in this case they use about 55% of the energy they get from the waste, from the heat. So they will release the other heat, about 45%. Okay, please see the example of a problem. A steam power plant produces about 50 megawatt while burning fuel to produce 150 megawatt of heat energy at high temperature. So determining the cycle thermal efficiency and the heat rejected in the cycle. So this power plant produces 50 megawatt of net work. So the work net is 50 megawatt, and the heat in, where they were burning, when they burn the fuel to produce heat in of 150 megawatt. So from here we have to calculate the thermal efficiency. So what's the thermal efficiency? Okay, please do the example. So we finish the part 2 of the chapter 5.